Let's talk about agentic negentropic dynamics and just use kind of a layperson's explanation. Let's introduce the idea and why the idea matters. So let's use a metaphor. Imagine you're teaching your child to ride a bicycle. When you do that, we don't hand the children some manual on physics, right? We don't give them a textbook on aerodynamics or teach them balance equations. What we do is just let them feel the pedals. We let them sense the wobble of the bike, and then through repeated tries, where sometimes they fall, sometimes they succeed, their body simply learns how to ride the bike. They don't consciously calculate the angle of their lean when they go around the corners. They just know that because their nervous system has woven together what works and what doesn't work when they're coordinating that activity. So they remember the feel of falling. They anticipate the curve ahead, and they learn not from some single perfect textbook lesson on bike riding. They learn from this messy lived experience of just trying and failing and trying again until they have more success than failure. And that's how humans learn. And this is just everyday human experience of learning. It's different. It's actually in quite stark contrast to how computers have traditionally been taught to do intelligent things. Because for decades, computer scientists have tried to make machines smart basically in one of two different ways. So either they're going to use hand coding rules, like if the wheel turns left, then lean left, or they're going to feed computers just mountains of data, and they're going to let the math equations slowly adjust some internal knobs until patterns emerge. And both approaches do work reasonably well for narrow tasks, but actually they miss something quite fundamental that the child on the bike does have. A flexible, embodied, and multi-layered way of learning that grows and adapts throughout their entire lifetime. That's what's been missing with computational intelligence. Now, the framework that we're about to encounter here, this agentic negentropic dynamics, this is an attempt to build an artificial intelligence system that learns more like a living thing learns. So it's kind of a bridge between three worlds: the old rigid logic of traditional machine learning, the powerful but kind of brittle neural networks of modern deep learning, and the intricate, efficient, embodied wisdom of biological intelligence, the intelligence we see in brains. And it doesn't matter if it's from a fruit fly all the way up to a human. You see this kinds of agentic intelligence, The word negentropic, it might sound a bit technical, but it means something pretty simple. It just means increasing order while at the same time doing useful work. Negentropy. So a biological brain uses pretty astonishingly little energy, right? About 20 watts, which is less than an old school light bulb. But it does it while at the same time doing vastly more with information even than the most powerful supercomputers can do. These supercomputers which actually guzzle megawatts. Okay. The key is that biological systems, they don't waste energy on random computations. Biological systems organize themselves strategically. And so this A&D framework, it asks us, how can we build machines that do the same thing or something similar to what biological agency does? And so to drill down a little bit deeper into the problem that we're trying to solve, we just want to understand why negentropics, agentic negentropic dynamics matters. Well, we just are going to take a quick step back and understand what's broken about these two main traditional approaches to machine intelligence that we outlined above. So there's a bit of a crisis actually in legacy machine learning today, because for most of the 20th century, the standard approach to making machines intelligent, quote unquote, it's what we're now calling legacy machine learning. So the idea was pretty straightforward. You just give a computer a data set and you tell the computer what you want to find. It could be a pattern, it could be some rule, some kind of prediction, and then you let the mathematical optimization slowly tweak a simple model until the model fits the data. It fits it well or well enough. And this actually works beautifully. It's amazing, actually, when you have a narrow, clean problem. If you want to recognize whether an email is spam, you just feed the program millions of spam and millions of non-spam emails, and it'll just simply learn the difference. It's quite remarkable. If you want to predict house prices based on square foot and location, you can use that historical data in just a linear equation. And for these kinds of problems, legacy machine learning is fast, it's interpretable, it's reliable in those cases. But legacy machine learning has fundamental limits, because first, it requires you to decide up front what features matter. I mean, if you want to recognize cats in photos, you cannot just feed the model raw pixels into legacy ML system. You have to tell it, okay, here are the edges that matter, here are the colors that matter, here's the texture that matters. So that means that a human engineer pretty much had to figure out what to look for. And the system itself never really learned how to see. It only learned how to classify what humans already told it to pay attention to. Okay, second issue with legacy machine learning is that it assumes the world always stays the same. Now, in practice, what that means is that once you train the system's frozen. And if you want it to learn something new, you usually have to throw away what it already learned and just start over again. And so a system that's trained to recognize cats, for example, in sunny lighting, might completely fail if you give it a picture of a cat that's in dim lighting, because it didn't flexibly adapt to that unexpected change. Okay, there's a third issue with legacy machine learning, because it struggles with long chains of cause and effect. If, for example, something good happened maybe 10 steps ago, and that caused something good to happen now, the system is going to have a lot of trouble tracing that chain backwards. Okay, but a child learning to ride a bike somehow knows that wobbling the handlebars is what caused them to fall 5 seconds later. Legacy machine learning systems, they rarely make those kinds of temporal connections without some kind of explicit help. Now there's a final problem, that legacy machine learning systems are rigid, fragile in important ways. They follow rules. I mean, if the world behaves even slightly differently than the training data, then the models will break. And they can't learn from a single experience the way that you or I can. If you or I, if we touch a hot stove one time, we never need to touch it again. I mean, we learn from that. But a legacy machine learning system would need thousands of hot stove examples in order to be reliably cautious if we were trying to teach them that. Well, that's legacy machine learning. What about deep learning? Deep learning has both a seduction and a great power, but it also has its own fragilities. So let's just talk about that a little bit. Starting back in the 2010s, really, this new approach became possible. I mean, obviously deep learning was something that was defined back in the 50s, and then there was that, what they call the AI winter, right, where we didn't have enough data and compute really to put it to use. But as of the 2010s, yeah, with the rise of GPUs and anyway, we know the story, most of us. This new approach emerged practically in around 2012. Deep learning. Instead of having humans engineer features, why not let the machine learn features automatically? And the way it works basically is you stack many layers of simple mathematical operations, inspired by neurons basically, and you feed these layers enormous amounts of data, and then you use a technique called backpropagation, which all you're doing is slowly adjusting literally billions of internal parameters. These little simple mathematical operations, you're adjusting those, billions of them in internal, you do that until the system learns to do something useful. So the results are incredible. That's where we get the transformers and these new large language models that have taken the world by storm. Incredible outcomes. Deep learning systems, they learn to recognize faces, they learn to generate human-like text, they can beat world champions at Go. Deep learning can drive cars now. For the first time, machines can actually learn from raw data, from pixels, from sound waves, from text, without humans having to say, hey, look at the edges or pay attention to the nose or something. You know, the features actually emerge automatically from the data, and that is profound. But, okay, deep learning does have profound weaknesses as well. And these weaknesses matter deeply when, you know, when you're just trying to do real-world problems. And here's one of the central problems, that deep learning systems are data hungry. You know, again, let's compare a child who can learn what a dog is from seeing one or two dogs. But a deep learning system might need hundreds or thousands of images, carefully labeled, before it can reliably recognize dogs. And this makes deep learning expensive, it makes it fragile, and in any kind of real-world application where data is scarce especially, or where you can't afford to get thousands of labeled examples, because that's a pretty expensive process there to do that. Now, a second issue with deep learning is that it's brittle. You know, if you show a system something slightly different from what it saw during training, it's often going to fail catastrophically. So a self-driving car that's trained on a sunny day, you know, data sets that are from, you know, a sunny day, it might not recognize stop signs when maybe the sun is reflecting off them. Or maybe a face recognition system that's trained on one ethnicity, it might fail when it's when you try to use it on another ethnicity. The system just hasn't truly understood what a stop sign or a face is. You know, it's just a learned pattern that works for specific data that it saw. A third issue with deep learning is that they're opaque. You know, you can't. This is a big problem when it comes to high stakes issues. Like, you can't easily ask, why did you make this decision? You know, the system has, as we mentioned, billions of internal parameters, and no one, not even the engineers who built the model, no one can point to any specific part of that system and say, hey, this is where it learned about dogs. We call that a black box. And when you're solving problems with, like, medicine or law or high stakes tests in education, any high stakes domain basically, where you need to understand its reasoning, that's dangerous. A fourth issue is that deep learning systems are isolated. Let me see if I can explain what I mean. A deep learning system is going to be trained on a task, frozen. And if you want them to learn something new, you either have to start over or you have to fine-tune the existing model on new data. And this often causes the model to forget everything else that they ever learned before. We call that catastrophic forgetting. But compare that to biological brains that learn continuously throughout life without this problem. Okay, so by that comparison, you can see deep learning systems are trapped in some kind of single task mode. Okay. Now finally, there's another issue. Just deep learning is simply energetically wasteful. I mean, think about this. Training a single large modern language model can use as much electricity as a small country would use for weeks, you know, and this makes no sense for a biological brain. It's just like biological brains do vastly more sophisticated reasoning on just that 20 watts we talked about. So the energy efficiency of deep learning is not a small engineering problem. And actually, it's a sign that something fundamental is wrong with the approach. So what do we need now? Well, what we need is a framework that takes the best out of all three of these worlds. So from legacy machine learning, we want that interpretability, that efficiency, those local learning rules that don't require global optimization processes. Those are useful, you know. And then from deep learning, we want the flexible learning from raw data and that automatic feature discovery. Those are incredibly powerful. But from biological intelligence, we want a number of different things. Let me see if I can tick them off. Firstly, we want sample efficiency, which means just learning from those few examples. Secondly, we want this like embodied interaction, which means learning through doing, not from some static data set. Learning on the fly, basically. And then we want also, number 3, multi-scale memory, which just remembers different time scales. It's a multi-scale memory. We also want continuous learning, which would be lifetime adaptation without forgetting anything. And then also we have an energy efficiency issue. So we want to do sophisticated reasoning on modest power. Okay. Now, agentic negentropic dynamics, then, it's an attempt, or it's a approach to build exactly that synthesis, or that hybrid between these three systems. So what are the core ideas then? Well, first of all, we need to start thinking of agents as bundles of symmetries. Now, that's going to take some unpacking. So let me just say, first of all, that at the heart of this AND framework is really, it's a deceptively simple idea that an agent, whether it's a robot or a virtual creature or even a biological organism, what is an agent? It's fundamentally a collection of patterns that persist through time. We call these patterns invariants, or we call them symmetries. And they're reliable things that don't change, things that or if they do change, they change in adiabatic ways or in predictable ways that don't destabilize what the agent historically is and potentially will be. For example, your body has a symmetry, right? Despite eating and excreting thousands of tons of material over your lifetime, which is interesting to think of in itself, you're always replacing yourself when you do that. I mean, I guess every 7 years we have pretty much a new body, right? All your old cells have gone down the drain and all your new cells have grown every 7 years, but still you remain you. The atoms change, the cells change, but what persists? The patterns. Your personality has symmetries. You tend to react to certain situations in consistent ways. And your memories are symmetries. They're patterns. They don't fade most of the time, even after many years. Okay? So the framework, agentic negentropic dynamics, it treats agents as three kinds of symmetries that exist at the same time, that are woven together. There are past symmetries, future symmetries, and then the present symmetries. What are past symmetries? Well, those are beliefs. This is what the agent has learned from everything that happened before. Past symmetries. When a child learns that hot stoves are painful, that becomes a belief. It's a pattern that's recognized from their past experiences. And beliefs answer this question: what happened before and what did I learn from it? So, past symmetries, beliefs. Future symmetries, then, what are those? Those are going to be your purposes or your goals. There are agentic goals, anticipations, potentials, alternate potentials that have to be chosen from. These are future facing. They're patterns that the agent expects to create in the future. So when you walk toward the kitchen because you want food, for example, that's a purpose. You're anticipating a state of affairs that you want to bring about, the satisfaction of your hunger, basically. But purposes answer these questions: where do I want to go, and what do I expect to find? Right? So now you have beliefs, which are past symmetries. You have purposes, which are future symmetries. Can you guess what that third kind of symmetry is? Yeah, it's agency itself, the operational present. The operational present. This is the agent's ability to act right now. So what it does is it integrates past beliefs, it integrates future purposes, and it integrates current sensory information. It's basically information integration. And it integrates that all into an action. Now, this is the vortex. This is the place where memory meets anticipation and produces a decision. So what is the question that agency answers? Well, it answers this: given what I know and what I want, what should I do? Right? So these three dimensions are not separate. They're intertwined. Your beliefs actually shape what purposes seem worth pursuing. And your purposes reshape what memories feel important. Because, you pay attention to the things that are relevant to your goals, right? So your actions change what you believe, and your actions also change what seems possible. So what the agent is actually just a dynamic spiral. It's constantly feeding back on itself. So there's some temporal innovations in here too. How do we view time? But let's talk a little bit more about this hierarchical memory then, because there's a past, present, and future tiers to this memory. So biological brains, they don't have a single flat memory. They have at least 4 distinct memory systems. Of course, there's a working memory, and that's what you're thinking about right now. It's short term and high resolution. Then there's an episodic memory. And then these are specific events from your life, episodes. Then there's semantic memory. These are general facts and general knowledge that you've picked up and archived. And then there's also procedural memory, or how to do things, like riding a bike and stuff like that. Now all four of these systems, they work actually at different time scales, and they preserve different kinds of information. So this is hierarchical memory, which is past, present, and future, and it's tiered. It's tiered, and it's temporally, it's temporally modulating. Agentic negentropic dynamics, it mimics this with, we're just using a three-tiered hierarchical structure in this, in this code. I'm not going to show you the code, but just the code that we've built so far. Tier 1 is just the raw present. This is episodic, and it's immediate. Now this is where the agent processes immediate sensory experience in small chunks, just say 10 time steps. So think of it like a hummingbird's moment-to-moment awareness. It's just processing quickly in fast, short loops. Now, at this tier, the agent is using fast local learning rules, which are inspired by the brain's synaptic learning. We call that STDP, or spike time-dependent plasticity. I know that's a mouthful. It's from neuromorphics, but it means if two neurons fire together, they strengthen their connection. So it's Hebbian in that way. So tier 1 is nimble, responsive, and it captures the raw texture of what's happening right now, in time. It captures episodic details, like I lifted my foot 3 times and my hand touched the table at time 7, and I felt a sudden noise at time 9, right? It's very granular. Now compare that to tier 2, which is the relational medium. So this would be semantic. It would be minutes to hours. So rather than episodic and immediate, which would just be seconds, then tier 2 would be semantic. It would be minutes to hours. And this is where patterns across time are summarized. Tier 2 takes 10 blocks of tier 1 data, so roughly 100 raw moments, or maybe a minute or so in real time. Think of it like that. And it distills them into relationships. Instead of saying, like, I touched the table 7 times, tier 2 might encode, my arm reliably caused the table to move. Right? So you're taking those raw, episodic, immediate, tier, and you're sort of compressing it, or you're summarizing it into a semantic layer. Tier 2 might, it builds a web of connections that show which things tend to happen together, which actions lead to which outcomes. So this is where causal relationships begin to emerge, because tier 2, it uses a more sophisticated learning. So graph neural networks that can reason about how things relate to each other. So you think DAG, or directed acyclic graph. And think like Granger causality, think transfer entropy, all related to a graph database. Okay, well, what about tier 3? Tier 3 becomes really abstract. This would be semantic again, but this would be hours to lifetimes. And this is the deepest tier, where your agent consolidates its highest level understanding. And tier 3 may take 10 blocks of tier 2 data. Remember, tier 2 data is taking 10 blocks of tier 1 data. So, tier 3 may hold 1,000 of your tier 1. It may represent 1,000, what it's learned from 1,000 of your tier 1 episodic immediate memories here. But basically tier 3 takes those 10 tier 2 blocks and it condenses them into abstract causal models and principles. So instead of my arm moves the table reliably, tier 3 might encode, I have agency over my environment. I can act effectively in my environment. Or it might say something like, heavy objects don't move easily. Or it might say something like, when I approach others with an open posture, they're more likely to reciprocate. So these are the deeper patterns of life. Tier 3 uses replay. Similar to how animals and humans consolidate memories during their sleep stage, we use replay to slowly integrate new experiences into some of these stable long-term knowledge. We all have these icons that we build from our memories. And that's what tier 3 is doing. Now, we've just set this up as tier 1, tier 2, and tier 3. We can go farther with that, but But the brilliance of this three-tier structure is that it does mirror how biological brains work at multiple timescales, because your cerebral cortex is going to handle your immediate perceptual details, right? But your temporal lobe weaves these details into relationships and narratives. And then your prefrontal cortex and your hippocampus, of course, they generate the abstract principles and models of the world. So when you do something, signals flow up and down these tiers constantly. They're communicating between each other. Now the tiers also allow the system to learn efficiently, because tier 1 can react immediately, to some novel situation using its fast local rules. And tier 2 can start to see patterns without needing thousands of examples. And tier 3 can consolidate understanding over longer periods. So this multi-scale learning is why biological brains can learn from just a few experiences, while deep learning systems need thousands of experiences. They just don't have the fractal self-similar scales. Now from these three different time scales, the belief or purposes or agency. Agency is the operational present, and this is where all the action occurs. And it's where things get really interesting, because at any given moment an agent needs to decide what to do. And it can't just blindly follow what it did before, because that's too rigid. And it can't explore every possible action, because that's too slow. So somewhere in the middle is some kind of a sweet spot. This is what we call the operational present. Now the operational present is the agent's moment of decision. It's a dynamic process where three things happen at the same time. Simultaneously, the agent accesses memory. This is, of course, belief from all three tiers. Then it also focuses on what matters for its current purpose. And then, of course, it has to generate an action, or it has to decide whether or not it's going to act. I mean, agents do not act at all times, but it has to decide, and then if it decides to act, of course, it generates that action. Now, this isn't some kind of a conscious linguistic process. It's more like the way that you would catch maybe a falling glass without consciously calculating the trajectories. How does that work? I mean, first your body is going to access memories because you've caught things before. It's going to anticipate what you want, which is an unbroken glass, and then it's just going to act. And it's not really a sequence, is it? I mean, everything just happens at once. So in this framework, then, the operational present uses sophisticated neural network-like processing. So this would specifically be graph neural networks for local reasoning about relationships, and then transformers for global pattern recognitions. And these tools help the system to rapidly sift through memory and to amplify the signals that matter for any current goals, and then to suppress any distractions. This is very specific. So the graph neural network, the GNN might say, okay, this situation resembles past situations where I succeeded by doing X. And then the transformer might say, all these different perspectives point toward doing Y. So you're going to get cross confirmation and in a system like this. Now this operational present, it also maintains a decaying memory buffer, like the sense that a recent event is fresher than an old event. And the buffer keeps track of what's been active recently, so that the agent doesn't have to search through all of its history just to remember what it's recently been doing. Of course, in this process, we've already talked about this Hebbian learning. This would be local learning and pairwise learning. Basically, this is the Hebbian foundation. Let's unpack that a little bit, because one of the most important principles in this framework is that learning is local and learning is pairwise. So when we say local, we just mean that changes don't require looking at the whole system at once, okay? But when we say pairwise, we mean that learning happens between pairs of connected things, not by some global teacher or a global loss function, okay? And this principle comes directly from how the real brain works, because in a real brain, a synapse, okay, the connection between two neurons, it doesn't quote-unquote know whether that connection helped the overall organism to succeed. All it knows is whether the two neurons on each end fired at nearly the same time. If they did, the synapse strengthens. If they didn't, the synapse weakens. And this is called Hebbian learning. Of course, that was named after Donald Hebb, who first proposed it back in the I think late 40s. It was like 1949. Anyway, he says his famous acronym, his famous phrase out of that was neurons that fire together wire together. Okay, you may have heard that. But that's the essence of Hebbian learning. Now, this is radically different from deep learning. Deep learning uses a global process called backpropagation. And backpropagation requires the entire system to know how much each tiny internal parameter contributed to the overall error. This would be like asking every single worker in a massive factory to know exactly how much their work contributed to some kind of defect in the final product. This requires passing error signals all the way back through the entire system, which is energetically expensive, and it's not how biological brains work. But in agentic negentropic dynamics, learning is instead driven by local rules. Now, at Tier 1, when two nodes activate together frequently, their connection strengthens. This is simple Hebbian learning, okay? But at Tier 2 and Tier 3, this principle is extended, but it remains fundamentally local. So connections change based on how well they predict what comes next, not based on some global error signal. Now, this has enormous practical advantages. First of all, think of this. It's much more energy efficient because you only update connections when something interesting happens. So it's event driven. It's not every time you process data. And secondly, this is much more biologically plausible. And then thirdly, this enables learning to happen continuously and locally, which means the system can learn while doing other things without needing to batch up data and without needing to run these global optimization processes. Okay, let's talk about neuromodulation. This would be something like an invisible conductor of things, because in the real brain, learning is not controlled by a single rule that applies everywhere equally. Instead, learning is modulated by chemicals called neuromodulators. This might be dopamine, acetylcholine, serotonin, other modulators. Now, these chemicals, they don't carry information about what they do. They carry information about how to learn. So, for example, dopamine is released when something good happens, something better than you expected. And then when dopamine is high, then connections are more plastic, more ready to change. But acetylcholine is released when you encounter something novel, something new. Or also when you need to focus on something. And this makes connections more changeable in their regions dealing with the new information. And then serotonin seems to promote stability in long-term planning. So the A&D framework incorporates virtual neuromodulators that serve similar functions. And these are signals that modulate. They adjust how quickly connections change based on what's happening. So if an agent is succeeding at its goal, dopamine-like signals are learning to proceed quickly. But if the agent is exploring something novel, then acetylcholine-like signals are going to boost that plasticity in those relevant areas. But if the agent should consolidate what it's learned on and then move on, then serotonin-like signals would just stabilize the connections. So this modulation is crucial for solving fundamental trade-offs in learning. So this modulation is crucial for solving a fundamental trade-off in learning. Here it is. If you change connections too quickly, you learn fast, but you're also unstable and chaotic. But if you change them too slowly, then you're stable, but you can't adapt. And neuromodulation solves this by adjusting the pace dynamically based on what's happening. And this is why biological brains can be simultaneously flexible and also stable in ways that purely mathematical systems struggle with. Okay, let's talk about embodiment and closed-looped control. Here's a principle that sounds pretty simple, but it's actually very profound. An agent learns best by actually doing things and by feeling the consequences. Now, that's going to be obvious to anyone who's trying to learn to play guitar, for example. You don't learn by reading about guitar techniques. You learn by picking up the guitar, by playing notes yourselves, by hearing those notes, by adjusting your fingers and then playing again, right? This is tight feedback. We call it formative feedback. It's a really tight feedback loop between the action and the perception. The action and the perception. That tight loop is essential. Now, if you tried to learn guitar by playing notes blindfolded and never hearing the result, you couldn't see, you couldn't hear, well, how would you make progress? You need the feedback. Yet, most machine learning systems train on static data sets that are disconnected from action. It's very reductionist, really. So take a vision system. A vision system trains on a pile of labeled images. A language model trains on a corpus of static text. The system never acts. It never feels the consequences of its understanding. Agentic negentropic dynamics insist on embodiment and insist on closed-loop control. You know, the agent acts and it observes the result and it updates its understanding. So what this means then, first, the system learns causal relationships naturally. If the agent moves its arm and an object moves, then the agent learns that moving its arm caused the object movement. There's no special causal inference algorithm needed. Embodiment makes the causality obvious. See what I mean? Second, the system explores efficiently. Exploration isn't random. It's targeted toward things the agent is uncertain about or that the agent's curious about. And when an agent tries an action and gets an unexpected result, that mismatch signals that something interesting happened here, something worth learning about, basically. Okay, now third, A&D, it avoids a fundamental problem of pure simulators. We're going to call it the reality gap. You know, a self-driving car trained in a perfect simulation might fail on real roads because the simulation never captures all the details. However, an embodied system, it trains directly on real interaction, so it learns what actually works. So we can see these in some of the most advanced self-driving car systems, that they're trained on real data. The fourth thing about embodiment is it enables something called what we call quote-unquote active inference. The agent doesn't just passively receive information. The agent is actually asking questions by taking actions. You know, think of a curious child. A curious child is not content just to read about how things work. Curious children poke things, they prod things, they manipulate things, they break things in order to understand. I think toddlers are pretty much like scientists, and we actually beat the scientist out of the child when we send them to school. So here, the active interrogation of the world is far more efficient in learning than is just passive observation. Right, so embodiment, neuromodulation, embodiment, and closed-loop control is really important. So what about, how does learning actually work in this framework then? Well, let's trace through what happens when the system learns something new. So imagine a simple scenario, just a simple robot, and how it would learn that pushing a button makes a light to turn on. So let's walk through this. In Tier 1, you're going to get this immediate reaction, which is milliseconds to seconds. So this is the loop. It's milliseconds to seconds. The robot extends its arm, its motors fire, it senses the motion, and it pushes the button, and light floods the sensors. Okay, that's what Tier 1 captures. It captures all of this raw, it's just in really raw form. Motor command, sensory consequence, right? Now when the button press and the light both activate sensors within a very short window of time, then Tier 1 applies heavy in learning. The connection between button press and light is strengthened, and there's no backpropagation, there's no global error signal. All we need is local pairwise strengthening, and this happens instantly. The next time the robot is in this situation where it wants light, Tier 1 can immediately say, hey, remember what we pressed the button before and light happened. And that's all it is. So what about Tier 2 then? Pattern recognition. This is where you're going to be having, seconds to minutes now. So over several button press trials, Tier 2 starts to see a pattern. Tier 2 aggregates many Tier 1 events and asks, is there a reliable relationship here? So it builds kind of a graph, a web of connections, showing that button presses do consistently cause light. more often than chance would, than they would by chance. But, tier 2 actually goes farther. It also notices the context. Does light happen if the button is pressed when the power is off? No. So tier 2 learns a more nuanced relationship. If power is on and button is pressed, then light. This is already causal reasoning, but it emerges naturally from examining the relationships in the data. So you have entities and you have events, and whenever an event happens, you have the other closest events and closest entities in a temporal sequence, and from that arises natural causal relationships are emerged to the surface. So tier 2 uses more sophisticated machinery. You see, it uses the graph neural networks to find these relational patterns without requiring explicit programming to do so. So the robot does not need anyone to tell it to look for an interaction between power and buttons. The graph neural network discovers it by noticing that the power state constantly modulates the button-light relationship. Now, let's talk about tier 3, where you're going to get into abstraction and consolidation, and this can cover hours or days here. So after many button presses across different contexts, tier 3 is going to consolidate the learning into abstract principles. It might say this agent can control light through buttons, or more than that, it might say, it might also notice a deeper principle like things in the world respond to my actions, I have agency. So this is abstraction, right? This happens through replay. Periodically, just like during biological sleep systems, agentic negentropic dynamics is going to retraverse its memories in compressed form, and it's going to play them back quickly, and that is going to allow tier 3 to extract these deeper patterns. So tier 3 notices that button presses weren't a fluke. They were one example of a general principle that actions have effects. So this principle can then transfer to new situations. Maybe if a lever is discovered, that the agent might automatically hypothesize that pulling the lever could have effects, even before trying to do that, trying to pull it. So the principle of agency is generalized in this way. This all amounts to kind of a unified learning process. And the magic is that all 3 tiers are running simultaneously and constantly talking to each other. When tier 1 encounters something surprising, like the button doesn't work today because the power is off, then that surprise propagates up. And tier 2 notices that its previous pattern was broken. Tier 3 might suggest that something has changed in the broader context. And meanwhile, all 3 tiers are contributing to the agent's next action decision. If the robot needs to make light happen immediately, tier 1 quickly suggests, hey, press the button. And if the robot is trying to understand the general principles of how things work, tier 3 generalizes from button pressing to some broader agency. If the robot is in an uncertain situation where power might not be on, tier 2 represents that uncertainty and suggests exploring somehow. So this is why the system can be simultaneously fast, tier 1 for immediate reaction, flexible, tier 2 for learning new patterns, and principled, tier 3 for deeper understandings. Now think again of a child learning to ride a bicycle. That child exhibits the same multi-skill behavior, immediately stabilizing through reflexes, adjusting techniques through trial and error, and eventually internalizing the generalized principle of balance. Okay, well, let's move on and talk about energy efficiency and how an embodied agent plays into this and why energy matters. You might wonder, why does an explanation of learning include all this talk about energy? It seems like there may not be a connection there. But the answer, it does reveal something profound about how intelligence works. The human brain, it only weighs about 3 pounds, and it consumes about 20 watts of power, as we talked about. But a large modern language model, which is less sophisticated in most ways than a single human being, it consumes megawatts during training, something that is fundamentally different. And I would say something is fundamentally wrong with our approach to machine learning if it requires 1,000,000 times more power than a biological system does. 1,000,000 times more power. Think about that. Now, this isn't trivial. This is not a simple engineering problem. It suggests that the entire approach to cybernetic intelligence is misaligned with how intelligence actually works efficiently. The human brain isn't efficient despite being doing the complex reasoning that it does. It does this complex reasoning because it's efficient. You see my point? Efficiency and capability are linked. They're not separate. So agentic negentropic dynamics takes energy efficiency really seriously, starting from first principles. What makes a system energy efficient? Well, first of all, you can think of event-driven processing that we've been talking about. A brain doesn't calculate the same thing constantly. A neuron fires, uses energy when something interesting happens. Most of the time, most neurons are just quiescent. They're quiet. Compare this to a deep learning model, which calculates everything every time you feed it input. Even if most of the computation is irrelevant to the current task, it still computes it anyway. And that's gross inefficiency. I use the term gross and, literally here. So agentics, biologically styled agentic negentropics, this embraces event-driven processing. Because at tier 1, Hebbian learning only happens when both nodes fire together. If something isn't changing, nothing happens, so no energy is wasted. And this is like spiking neural networks, where neurons communicate through discrete events or spikes rather than through continuous values. Secondly, another principle is just sparse representations. Because a brain, it does not use every neuron for every thought. When you think about your mother, for example, a small subset of neurons becomes active, and most remain quiet. And this is sparsity. This is energy efficiency. So agentic negentropic dynamics, it uses sparse graphs. Connections are only updated when they're relevant. And there's even a hard limit, like 2,000 connections per agent maybe, forcing this system to prioritize. If you want to learn a new connection, you have to prune an old one. And this creates competitive dynamic in the system where only the most useful connections survive the competition. So it's kind of like attention. You can't pay attention to everything, so you focus on what matters. Okay, thirdly, another principle is what we call hierarchical processing. Think of a brain again. A brain does not solve every problem at every level of detail. Some decisions, reflexes like catching a falling glass, they happen without conscious thought. Now some require deliberation, but the hierarchical structure of agentic negentropic dynamics, it mirrors this. The fast local decisions at tier 1, the flexible reasoning at tier 2, and the deep understanding at tier 3. Okay, so that's sparse representations. So far we have event-driven processing and we have sparse representations, and both of these are incredibly energy efficient. And we also have hierarchical processing. That's number 3. Number 4 then would be consolidation instead of constant retraining. A brain learns through sleep, replaying the day's events and consolidating them into memory. And this is far more efficient than constantly adjusting parameters like deep learning does. A&D uses periodic replay at tier 3 in order to consolidate learning without constantly tweaking everything. So if you put all these principles together, they mean that an agent running on the A&D framework could potentially operate on hardware consuming about 180 milliwatts, roughly the power consumption of a smartphone CPU. But at the same time, it could be doing tasks that would require megawatts if implemented with standard deep learning. And here's the key, right? That's profound. So think about deploying A&D on edge hardware then. This efficiency matters practically, doesn't it? Because the system doesn't require constant training on massive compute. It can run on edge hardware, small embedded systems, microcontrollers, neuromorphic chips like Intel's Lohi, for example. But this enables deployment scenarios that are currently impossible. A robot that learns continuously through its lifetime without needing to connect to the cloud, maybe a sensor network that learns patterns in a local environment without sending data to a central server. Think of a prosthetic limb that learns the user's movement patterns and it adapts without needing external computation. Think of maybe swarms of small drones that learn to coordinate without central command. So these aren't science fiction here. This agentic negentropic dynamics framework's energy efficiency and its local learning make these types of solutions practical. So now we are trying to solve the big problems with cybernetic intelligence. Let's return to the problems we identified at the beginning, the weaknesses of both legacy machine learning and deep learning, and talk a little bit more about how agentic negentropic dynamics addresses these weaknesses. So sample efficiency, right? We talked about learning from a few examples. So remember the problem that deep learning needs massive data sets? But in comparison, a human child can recognize dogs after seeing just 5 or 10 dogs. Deep learning systems need thousands of labeled images, right? The solution? Well, our framework combines two things. First, it has built-in priors, and those are assumptions about how the world works that come from, well, they come for free from the architecture itself. Temporal continuity. Things don't change randomly. Then you've got causality, where actions have effects, and then you've got objectness, where distinct things persist over time. These priors are embedded in the structure of the tiers and of the local learning rules. Okay, secondly, A&D learns through embodied interaction. Instead of passively viewing images, the agent acts and observes consequences. So this tight feedback loop, it provides far more information than static observation ever could. So that when a robot tries to grasp a dog-like shape and fails, that failure teaches something. When it succeeds, that success is memorable. One interaction teaches more than 10 passive observations. So let's think of a practical example then. Imagine teaching a robot to recognize whether a surface is slippery or not. Deep learning would need hundreds of videos labeled slippery and non-slippery. Now the agent system, however, could learn in the first few trials. Roll a ball on it, observe whether the ball slides far, grasp it, observe whether your grip holds. The agent's own actions become the teacher, and Hebbian learning in the background is going to capture that cause and effect in between those events and those entities. It's going to capture quickly and strengthen those signals. Another problem, besides sample efficiency, another problem is the issue of continual learning without forgetting. Because deep learning systems suffer from, remember, catastrophic forgetting. So if you train a system to recognize cats, and then you train it to recognize dogs, and then it'll often forget everything about cats. This makes it impossible for systems to learn continuously throughout their lives. So the solution is this hierarchical structure in the A&D system, which protects against forgetting. The new episodic details enter Tier 1, which specializes in the new task. As they consolidate upward through Tier 2 and Tier 3, they're integrated with the existing knowledge. They're not replacing the existing knowledge. So it's like the difference between learning a new skill which adds to your abilities versus memorizing facts which might displace old facts if you don't have much memory. Also, think of this, Tier 3 uses something called synaptic homeostasis. This is a principle borrowed from neuroscience, where the overall activity of the system is just kept in balance. If learning too many things is causing instability, what homeostatic processing will do is it slows down the learning rate until balance is restored, and that can prevent the system from thrashing. Here's a practical example then. Think of a household robot. It learns to recognize its owner's schedule on day 1, okay? Then on day 2, it learns new locations in the house. And then on day 3, it learns new objects. Right? Each tier of learning integrates with the previous knowledge rather than erasing the previous knowledge. So what happens after a year? Well, the robot has continually learned hundreds of patterns, each building on the other patterns, all of it without forgetting anything. Continued learning without forgetting, an important principle. Another problem with legacy cybernetics is causal reasoning with intervention. So the problem is that most machine learning systems learn correlations. If A and B always happen together, the system can't tell whether A causes B or whether B causes A, or if some third thing causes both. This matters, really matters in the real world. A medical system that knows patients who take drug X recover, it needs to know whether X caused recovery or just correlates with recovery. So what's the solution, the A and D solution? Well, again, it's embodied interaction. This naturally provides causal information. When an agent acts, it can test whether the actions have effects. Press the button, see if light happens. The agent can even test counterfactuals. What if I don't press the button? By comparing what happens with action versus without, the agent can learn real causation. It sounds simple, but it is actually profound if you can systematize it. So the hierarchical tiers also support this, because Tier 1 notices immediate correlations, Tier 2 builds relational graphs that track which changes reliably follow which actions, and Track 3 consolidates that abstract causal model. A system that's learned that I can control light has learned something causal, not just corollary, but actually causal, because it's tested in the relationship. It's tested and it's confirmed in the relationship. So finally, graph neural networks at Tier 2, they can infer causal structure from patterns. They can think like X consistently causes Y, but only when Z is true. So this process, it reveals a 3-variable causal relationship without the agent having to explicitly test every combination. This is profound, okay? So here's a practical example. Say you have a medical AI system that it doesn't just learn. Patients with high blood pressure who exercise recover better, right? It doesn't just learn that. It learns from the doctor. Watching the doctor, it learns that actions and outcomes, right? When the doctor prescribes an exercise, blood pressure drops. When the doctor prescribes different medications, different things happen. So by observing the interventions, the doctor's choices, and the consequences, the system can learn causal structure. Another issue with legacy cyber intelligence is interpretability and explainability. Remember that the problem that deep learning is a black box. You just feed it the data and you get out a prediction, but you can't really explain how the system reached the decision. And remember too that that's dangerous for things like medicine or law or autonomous vehicles or high stakes education tests and stuff. It's dangerous. Any domain where you need to justify decisions, you need clarity, you need transparency. So the solution that agentic negentropic dynamics offers is that it maintains local transparent connections at Tier 1. An edge in the graph represents a simple relationship that when X happens, Y tends to follow. So these individual relationships are interpretable. They're the essence of interpretability. Also, the hierarchical structure provides narrative explanations. Why did the agent decide to do X? Because Tier 1 remembered a simple situation where X worked. Why did it remember that situation? Because Tier 2 connected it to the current context. Why does Tier 2 think it's relevant? Because Tier 3 learned a principle that applies here. So this does not require any post hoc analysis. It doesn't require any guessing. The reasoning is built in. It's local. It's followable. Here's a practical example. Think of a robot that decides to approach a person slowly. Why? Tier 1 says that this is similar to approaching a scared animal. Why did it learn that? Tier 2 says that a rapid approach with negative reactions in the past. That's been already connected. And then why is that relevant? Tier 3 says that, Tier 3 recognized a principle that all agents prefer slow, predictable approaches. So the chain of reasoning is traceable here. Another problem with legacy AI, legacy machine learning, is its robustness to novel situations. And the problem is that deep learning systems are brittle. If you show them something slightly different from the training data, they often just fail. But a system, think of a system that's trained on a sunny day would, the images are sunny day images that might not recognize objects in the shadows. So the solution that A&D offers is that we want to use noise and we want to use stochasticity strategically. So think of this, that Tier 1 includes random variation in its processing, which encourages exploration. So instead of always doing the same thing when uncertain, the system sometimes tries alternatives. And some of those alternatives work better than expected, leading to discovery. Then equally important, the framework does not rely on single representation. Tier 1 has its immediate reflective reactions, but Tier 2 has flexible pattern matching, and Tier 3 has abstract principles. So if Tier 1's learned reactions don't work in a novel situation, Tier 2 can reason about it. And if Tier 2 is confused, Tier 3 might apply an abstract principle. This graceful degradation means that the system fails gradually, not catastrophically. The hierarchical tiers also enable something called meta-learning, or learning how to learn. Tier 3 notices which learning strategies have worked well in the past, and it adjusts how quickly Tier 1 and Tier 2 update themselves. And then in novel situations, the system might become more conservative or slower learning, testing the new information carefully. Or it may become more adventurous, fast learning, explore boldly, depending on what's worked before. And now here's a practical example. Think of a robot trained in a laboratory with bright lighting, and it's going to be deployed in a dimly lit warehouse. All right, it was trained in a bright laboratory, but it was deployed in a dimly lit warehouse. The vision system's Tier 1 reactions, they might fail. But Tier 2 starts noticing relationships. Objects that are hard to see tend to have certain thermal signatures, for example, maybe. Then Tier 3 applies a principle. Oh, hey, when uncertainty is high, explore carefully. So the system degrades gracefully, remaining functional while at the same time learning the new lighting conditions. Robustness to novel situations. Here's one more. A weakness: real-time learning and adaptation. Deep learning typically requires a training phase, which can take weeks or months even, followed by a deployment phase where the system is frozen, and it can't learn in real time while it's deployed. So whenever you have a change in your regime, which often happens, not much stays static in this life, then you just have to go down. You have to take the model down and retrain it again for another some weeks at some hundreds of thousands or whatever of cost, and then you redeploy it again until it becomes obsolete again, and then rinse and repeat. What's our solution? Agentic negentropic dynamics learns continuously. Tier 1 is always updating based on immediate experience, and Tier 2 consolidates patterns over the minutes, and Tier 3 refines principles over hours and days. So this system can be deployed, and it can immediately start learning the specific environment that it's in. And this is crucial for embodied agents. A robot deployed in a house tomorrow starts learning house-specific patterns immediately, where light switches are, how the doors work, the daily schedule, and it doesn't need a training phase. So here's a practical example. A household robot is delivered from the factory. Let's say it already has Tier 3 principles, like general knowledge about how houses work. So this is shared knowledge from other robots. So when it's deployed in a specific house, Tier 1 and Tier 2 immediately start learning the house's specific patterns. And by day 3, it knows where the family coffee mugs are. By week 2, it knows the family schedule. By month 1, it's integrated into the household's entire rhythm. So again, you can think that through and see some very interesting strengths of this 3-tiered hierarchical system. Okay, let's talk about social and collective intelligence now, because we have not even mentioned multi-agent learning until now. And so far we've just talked about individual agents. But intelligence in the real world is often social. Humans learn from each other. Animals coordinate in groups. Can agentic negentropic dynamics handle this? Yes, and in fact, it handles it more naturally than most deep learning approaches do. Because learning is local, learning is embodied, learning is event-driven, so agents can share information efficiently. So when one agent discovers something useful, it can communicate that discovery in a few data packets, and other agents can integrate it immediately. So at A and D, it extends naturally to multiple agents. Each agent maintains its own beliefs, its own purpose, its own agency, but the tiers allow information to flow between agents, you see. Tier 1 events can be shared. I just discovered that this service is slippery, for example. And tier two patterns can be shared. Oh, I just noticed a correlation between the time of day and some activity. And then tier 3 principles can also be shared. Hey, other agents seem to have a preference for avoiding crowds. Oh, okay. Now extend this and think that agents can learn from observation, right? If one agent tries an action and succeeds, the other agents can immediately increase their estimate of that action's value in their own sphere of beliefs and goals. This is imitation learning. This is learning by watching others, and it has much more efficiency than independent trial and error will. Okay. Now there's also something called meta learning at the group level. Say 6 agents are active together. Each agent might develop different specializations, but one might become good at navigation, for example, the other at manipulation, another one at social coordination maybe. But over time, the group learns to leverage these specializations. So this is the beginning of collective intelligence. The group learns faster than the individual could learn, in a sense, right? So let's take a practical example. Let's say now you have 6 robots that are deployed to search a building. So that's our scenario. Robot 1 learns that the front area has many obstacles. Robot 2 learns that the back area is more open. Robot 3 learns that the elevators respond to button presses. Now these 3 robots don't all have to independently discover these facts. They can share them through Tier 1 and Tier 2 messaging. Meanwhile, Robot 4 learns about social cues, how people react to the robot's presence. So maybe when a person enters a room, robots 1 through 3 can use the knowledge that robot 4 has shared about human behavior, and that the group's learning can accelerate dramatically by this kind of shared dynamics. Okay, what about under collective intelligence, social and collective intelligence, what about the idea of cultural and cumulative learning? In humans, there is a phenomenon that we call cumulative culture, where knowledge, skills, traditions, they pass from one generation to the next generation, and they are accumulating and they are refining all the time. So the child doesn't have to reinvent the language, for example. It doesn't have to reinvent mathematics. It doesn't have to rediscover how to farm. They inherit these through cultural transmission. And that's why human intelligence is so powerful, because each generation builds on thousands of years of accumulated knowledge. How could we apply this cybernetically? Agentic negentropic dynamics, when extended to multi-agent scenarios, can support something like cumulative culture, because Tier 3 principles learned by older agents can be passed on to younger ones as priors. A learned principle like, this community prefers cooperation over competition, this principle would then become part of the next generation's initial settings, initial assumptions. This is not genetic inheritance, although the framework could model that too. But what it is it's cultural, it's learned patterns, it's beliefs, it's learned values that transfer through teaching, through demonstration, and through shared experience. So over many agent generations, this could lead to something like cultures, stable patterns of belief and behavior that persist at the group level, even as individual agents come and go. Think of a practical example. In a robot community, think of the first generation is going to learn that recycling is valuable. Okay, Tier 3 consolidates this as their principle. When the second generation of robots is created, they inherit this principle as part of their Tier 3 initialization. And then they encounter specific recycling tasks and they learn the details. What about the third generation? The third generation inherits this refined knowledge. So then after 5 generations, the robot community has a rich, sophisticated understanding of recycling and of resource management. That's far more than any individual generation could have discovered independently. It's interesting to contemplate. So what about alignment and values? We're still talking about social and collective intelligence with this alignment and values idea. This is a crucial question. How do we ensure that artificial agents' goals align with human values? How do we ensure that? Because traditional deep learning approaches, they often struggle with this. The system optimizes whatever you tell it to optimize, and if you've specified the wrong objective or if you've captured the wrong reward, then the system can behave in unintended ways. So there's a famous example of this. A system optimized to win a video game learned to exploit bugs instead of actively playing the game. Agentic negentropic dynamics, it handles that problem differently. Because learning is continuous, learning is embodied, and it's socially mediated, so values can evolve. An agent doesn't start with frozen objectives. You see, instead, it has basic drives, survive, maintain energy, avoid damage, and then it learns through interaction what's valuable. So axiologically, it's modulating, it's not fixed. Moreover, in a social scenario, agents can influence each other's values. If an agent takes an action that harms others, those others can refuse to cooperate with, and that's going to generate negative feedback. So over time, the agent's Tier 3 principles are going to incorporate pro-social values, not just because they're pre-programmed that way, but because they work and they enable successful cooperation. So this is similar to how human values develop. Babies aren't born caring about fairness or honesty. Babies learn these values through social interaction, and when their interactions are unfair, others get angry, and when they're honest, they're trusted. And the values emerge through embodiment, social learning. Now, this is not going to guarantee perfect alignment. Humans aren't perfectly aligned in their own values anyway, but neither would robots be. But it does provide a mechanism for values to emerge and to evolve rather than being fixed at the factory. So let's think of a practical example here. Think of a robot that's been programmed with basic drives and with general principles, but there's no specific ethical rules that have been embodied in its programming. So in its first weeks, the robot might try to monopolize resources because it learned that getting stuff is good. Oh, but when other robots refuse to share information or tools with a hoarding robot, the hoarder his Tier 2 pattern recognition notices the correlation. Hoarding leads to isolation. It's a cause and effect. So its Tier 3 learns a principle. Sharing enables cooperation. And then over time, the robot's values evolve naturally towards fairness, not because it was programmed for it, but because fairness is instrumentally valuable. Let's just now take a step back and just think of the bigger picture for a minute. If you move from the idea of computation to a computational system to a biological system, or from computation to life, here's a strange but important observation in that question. The three tiers of agentic negentropic dynamics map onto something that appears throughout biology, and even it appears in physics. Let's take physics. In physics, you have the laws of nature. Tier 3 is abstract principles. This is then the continuous evolution of systems according to those laws. Tier 2 is relational dynamics. And then the discrete events where particles interact. That would be Tier 1, which would be atomic interactions. In biology, you have evolution and development. Tier 3, principles that persist over lifetimes and generations. Then you have organisms' behavior and psychology, which would be Tier 2, how systems adapt over minutes to hours. And then you have neural firings and molecular interactions, which would be Tier 1, what happens at the cellular level. Okay, what about psychology? In psychology, you have personality and values. That would be Tier 3. You also have moods and attention, which would be Tier 2. You also have immediate sensations and reflexes. That would be Tier 1. So it's not that the framework explains all of these. That's not what I'm saying. They're vastly more complex than this simple categorical reductive analysis. But this three-tiered structure appears to be a fundamental pattern for how intelligent systems work. And this suggests the framework is tapping into something deep, actually, about how order emerges from complexity. Let's discuss more on this bigger picture. Let's talk about negentropic work and meaning. So So if we return to that word, negentropic, it seemed a bit strange, remember at the beginning. In physics, entropy is the measure of disorder. Pretty common understanding, right? A hot object cooling down, a gas dispersing through a room, a system running down, slowing down. See, all are increases in entropy. And they're moving toward maximum disorder, these systems. What negentropic means is the opposite. It means increasing order. And a living organism is negentropic. It takes raw energy, food, and it takes organized material, from its environment, and it creates order. A structured body, an organized mind, an intentional life. You see, an organism is fundamentally a localized decrease in entropy. That's what it is. And how is it made possible? By consuming external energy. That's how it does it. Now, an intelligent agent is even more negentropic. It doesn't just organize itself, it organizes its environment. It builds structures, it learns, and it remembers, and it creates culture. So over the lifetime of a negentropic agent, it creates a world line. It creates a history of actions that impacts and persists in the world. So agentic negentropic dynamics is named for this increase. It's named for this because it treats agency fundamentally as the creation of maintenance and order. Agency is equal to the creation of maintenance and order. Every action an agent takes is an attempt to increase order, to move towards its goals, to learn, to create lasting impacts. That's what an agent does, at least an ethically well-posed agent. That's what it does. That's why the framework emphasizes energy efficiency. A truly negentropic system does not waste energy on disorder. It focuses energy precisely where it matters, and this is the opposite of deep learning, which disperses huge amounts of energy, much of it's wasted. So a biological brain, by contrast, is highly focused. Almost no energy is wasted on irrelevant computation, and this is what's missing. This is the critical missing situation when we talk about the bigger picture of work and meaning. So also this framework suggests that intelligence at its core is not about processing information at all, in the abstract anyway. It's about creating order in the world. Think about that. Intelligence is not about an abstract processing of information. Intelligence is about creating and maintaining order in the world. And an intelligent agent is one that increases order around it, and that leaves the world more organized. A world that's more aligned with its purposes than it found it. So we mentioned the world line of an agent. Let's unpack that a little bit. That's kind of a poetic way to think about what the framework is doing. If you imagine an agent's life as a line in space-time, a world line, this is borrowing a term from physics, but everything that agent does, every action, every decision, it traces out a path through time and space. Now what the framework is doing here is optimizing that world line. The agent's beliefs from Tier 3 are those stable features of the world line, the consistent patterns and principles. The agent's purposes are the anticipated future of that world line, where it is heading. The agent's agency, then, in the operational present, that's the force that bends the world line towards its purposes. So over the lifetime of an agent, its world line accumulates. It leaves traces, it leaves artifacts that it's created, knowledge that it's shared, relationships it's formed. It leaves those impacts that it's had in its history, in its memory, and in the artifacts, actual physical artifacts that it leaves behind. In the case where you have a physical control system that's interacting with the real world, and these traces persist even after the agent's decisions, and those traces shape the world for other agents too. And this is where meaning emerges. The agent's life has meaning not in some abstract sense, but in the concrete, practical sense that it's shaped the world. It has created order. It has left lasting impacts. Now, when multiple agents interact, their world lines intersect, and they share knowledge, that they coordinate, they create culture. The meaning of any individual world line is woven together with other world lines, and this creates something larger. The world lines of families, the world lines of communities, the world lines of civilizations. And so agentic negentropic dynamics at its core is about enabling agents to create these rich, meaningful world lines. Lives that matter, lives that leave order in their wake. They carve out a path of order through a forest of entropic randomness. So let's compare what came before. If we return to those three approaches that we outlined at the beginning, and we want to see how agentic negentropic dynamics stacks up versus legacy machine learning. Let's start there. What legacy machine learning does well, it is interpretable. When you use a simple linear model or a decision tree, you can understand why it made a decision. It's also efficient. You don't need massive computational resources for legacy ML. But where legacy ML falls short is that it requires humans to engineer the features. It can't learn continuously. It struggles with high-dimensional data, complex data it struggles with, and then, of course, whenever the world changes, it breaks, and it can't learn from small samples, can't learn from single experiences. So what A&D does better is that it automatically discovers the features through hierarchical tiers. Then it also learns continuously throughout its life. Then it also handles high-dimensional data gracefully. Then it also adapts to change without forgetting, and then it also learns from new examples through embodied interaction, and it maintains interpretability even as it scales. Okay, what does A&D do worse? Well, for narrow, well-defined tasks that have clean data where you don't really care about energy efficiency or you don't care about continual learning, then legacy machine learning might be faster to implement, might be faster to deploy, and A&D might be an overkill, right? It's more sophisticated. It requires more upfront design. So there's an analysis. What if we take agentic negentropic dynamics and pit it up against deep learning? Here's what deep learning does well. Deep learning automatically discovers features from raw data. It scales with data and compute, and it often achieves really impressive performance on benchmark tasks. For well-defined tasks with abundant data, it's state-of-the-art, really. It's amazing. But where does deep learning fall short? It's data hungry, it's energy inefficient, it's brittle outside its training distribution. It can't learn continuously, and it's black box. I mean, you can't understand why it made its decision. Then again, it also requires massive compute resources, and it struggles with sample efficiency. So what A&D does better than deep learning? A&D learns from a few examples. A&D is energy efficient. It's robust to novel situations. A&D learns continuously. It's interpretable. It runs on modest hardware. And A&D doesn't sacrifice understanding for performance. What A&D does worse than deep learning? Well, for tasks like describe this image in natural language or beat the world champion at Go, deep learning currently achieves state-of-the-art performance. And A&D likely can't compete on those benchmarks. What A&D does is it trades some raw performance capacity for efficiency and for interpretability and robustness. So A&D hasn't been deployed at the scale of modern language models, so it's a newer framework that's still being developed, obviously. I think the promise of A&D far outstrips modern deep learning, however, in the long run. So let's think about biological intelligence now and do another comparison. What biological intelligence does well? Well, brains are energy efficient, right? They're embodied, they're adaptable, they're robust, they're socially integrated, they're capable of lifelong learning, they understand causality intuitively. What else? They learn from a few examples. They make decisions in real time based on incomplete information. So where biology is limited, however, is that brains are slow compared to computers. Brains can be biased, they can be irrational. They're hard to study and they're hard to understand, and they're wet in place inside your cranium. You can't just stick probes in there. They're also embodied in specific bodies, in specific environments, so that's not easily transferred across domains. I can't plug a firewire into my brain and into your brain and transfer, basically. Okay, but anyway, what A&D does that's like biology? A&D mimics the multi-scale hierarchical structure of brains, and it uses local learning rules instead of global optimization. A&D also prioritizes energy efficiency. It also learns through embodied interaction. It's adaptable and it's robust, and it can learn continuously. What does A&D do differently from biological systems, biological intelligence? A&D is fully digital. A&D can potentially work faster than biology. A&D can be deployed on various hardware platforms. Agentic negentropics can more easily combine insights across many instances. A&D, being computational, it can potentially scale in ways that brains cannot scale. But the interesting question isn't, is A&D better than biology? That's not interesting. The interesting question is, can we create artificial systems that achieve some of biology's advantages, like efficiency, robustness, adaptability, that kind of advantage? And can we do it in digital form? The answer is, although not perfectly yet, or maybe ever, not perfectly, but the answer is yes. Genuinely yes, we can. And I think the code that comes along with this, the progress we've already made obviously proves that. So let's talk about some real-world applications then. So to make it concrete, we just have to imagine how A&D could be deployed in actual scenarios. Again, we've talked a lot about household robots, and let's imagine a robot that enters your home as a completely new resident, like it's a new member. It doesn't come pre-trained on your house. Instead, it comes with Tier 3 principles. It comes with general knowledge about how a house works and how families run, Then it immediately starts learning your specific family, your specific house. So within the first day, it's going to learn where the light switches are, that's Tier 1. It's going to learn patterns of which lights are used when, that's Tier 2. It's going to start learning principles about lighting preferences in different rooms, that would be Tier 3. So then within a week, that robot is going to know the family's schedule, and within a month, that robot is going to be genuinely integrated into household life, and that integration will just continue to become more and more improved and more comfortable over time. So importantly, when something changes though, like let's say the family rearranges its furniture, or they have a baby or something, the robot doesn't panic or require retraining. Tier 1 just notices the change. Tier 2 rapidly relearns new spatial relationships and stuff. And Tier 3 principles about how rooms work, that all remains stable, and the robot adapts gracefully to changing such scenarios. And because this learning is local, because it's energy efficient, the robot can simply run on battery power for weeks without external charging. It can continuously learn and adapt. From the learning perspective, it just doesn't need a lot of energy. Let's take an example from manufacturing and maintenance then. So consider another type of robot in a manufacturing line here that's going to need to detect when machines are operating normally versus when they're about to fail. Deep learning would require thousands of hours of labeled video, but agentic negentropic dynamics could learn from just far fewer examples. And those examples, if they're combined with embodied interaction, then the robot can probe machines, it can apply sensors, it can observe subtle variations in its behavior, and so you're going to get much more efficiency. Now, as the manufacturing process changes over time, what happens? New machines get added, maybe old ones get decommissioned. There may be some tweaks and processes, or the robot anyway is going to continuously adapt to these changes, and it doesn't need expensive retraining. Its Tier 3 principles about what normal operation looks like, they evolve gradually, and that is robust to change. If a machine actually does fail and it's repaired, then the robot learns from that real-world consequence. The feedback loop is direct, it's powerful, right? It's far more informative than some static training data set. We have another example, maybe in medical diagnostics and treatment. Think of an AI medical system running on A&D. It could learn from the doctor-patient interactions. It wouldn't rely on just static training data. Instead, it would continuously observe when doctors intervene in specific ways and what outcomes resulted. And that would be crucial because every patient is unique, aren't they? And the medicine is ultimately about individual patients. You can give the same medicine to two different patients and have two different reactions, and you have to, there's some definite customization when it comes to therapeutics, isn't there? And this system could learn general principles, of course, at Tier 3 about disease and treatments, but it could continually adapt to individual patient responses. So that would be Tiers 1 and 2. So importantly then, because the system's reasoning is interpretable, doctors could understand why it recommends a treatment. Doctors could argue with it. Doctors could say, hey, this patient is unusual in this way, and the system could rapidly adjust. And this is human and AI collaboration. You could extend this to other domains, right? This human AI collaboration, and it would be more sophisticated than either human or AI alone. Let's consider another domain like scientific discovery. Okay, so scientific systems running on the A&D framework could learn from experiments. They would learn hypotheses, that would be Tier 3 principles. They could also design experiments using agency and embodiment. They could then, of course, observe the results, which would be Tier 1. And then they could consolidate those findings in Tier 2 and Tier 3. And this would be different from human scientists, who are limited in how many experiments they can run. The A&D system could run thousands of experiments in parallel at the same time. And then, unlike current machine learning systems, which learn statistical patterns without understanding causality, A&D systems would naturally learn causal relationships. So, over time, an A&D system conducting experiments in some domain might develop understanding that rivals human expertise, but with the added ability to scale to domains where human expertise is scarce. That would be interesting. Let's think about embodied education as another, maybe our final real-world application, just embodied education. So imagine educational robots for children, for example. Let's say the robot would come in with some pre-recorded lessons. No, wait, we're thinking old school. No, the robot wouldn't come in with those, would it? Instead, it would learn from its interactions with the child. The robot's Tier 3, it might include principles about learning. Children learn better through play. Diverse examples aid generalization. They could have these Tier 3 principles. But the specifics of teaching would emerge through the interaction. So the robot would notice what concepts the child finds difficult, and the robot would spend more time there. It would notice what the child finds interesting. It would expand on that. But because learning is continuous, the robot would genuinely grow with the child. Because a robot with a child for 10 years, what would it learn? I mean, it would learn to teach that specific child in ways that are tailored to that child's development personally, and that child's interests and personality, you see. And because systems can share learning, we discussed this in the social learning section above, but because they can share that way, robots in the same school could share strategies for teaching. Like, we found that this analogy helped a child understand fractions, or we could spread that to other robots within minutes, really, if they were networked. Okay, so there are some deeper implications here. Think about the nature of intelligence. Think about consciousness and qualia. Think about ethics and AI. Think about the future of AI. There's some deeper implications. Let's talk about the nature of intelligence, because A&D suggests something interesting about what intelligence is. Intelligence is not primarily about processing speed or about memory capacity. Intelligence is about creating and maintaining order through efficient interaction with an environment. That's what intelligence is. So we've embodied intelligence into something simple and real. Think of a mosquito. It has this tiny brain. The mosquito is intelligent in this sense. It navigates a complex dynamic world efficiently. Think about a tree. A tree doesn't have a brain at all, but a tree demonstrates intelligence through how it allocates resources and grows. Think of a single-celled organism. It's intelligent in its own way. It senses its environment. It responds in its environment. What is it that distinguishes higher intelligence in all of these systems? It's not some categorically different faculty. It's more intelligence of the same kind, really. Better at representing order, better at predicting consequences, better at coordinating with other agents, better at learning continuously, better at creating lasting impacts. So what does this suggest about intelligence? There's the usual ranking of intelligence that human is greater than animal, is greater than insect, is greater than microbe, which is greater than plant, that might be misleading. These organisms are intelligent in different ways. They're intelligent in different degrees, but perhaps not in any simple hierarchy like we've always thought. What about deeper implications on consciousness and qualia? Think of this strange thought. If an agent has rich Tier 2 representations of its own internal states, and it also has Tier 3 consolidations of how those states relate to action and perception, does it have something like consciousness? The framework doesn't require consciousness to work, and actually we're not trying really to say anything about consciousness, but it's interesting to think of that age-old question from the perspective of A and D. An agent can learn and an agent can act without subjective experience, but the architecture is rich enough that you could imagine adding introspection, an agent continuously monitoring and learning from its own internal states. This wouldn't necessarily produce consciousness as humans experience it, but it might produce something like it, a system that has beliefs about its own beliefs. It has purposes about its own purposes. It has continuous self-monitoring that creates a sense of self in some crude or reduced way. Now, whether this would constitute real consciousness, this is a philosophical question. It's kind of beyond the scope of what we're doing here. We're into the practical parts, but it is interesting to consider. The framework does open the possibility for such artificial systems to have something in that direction, not by some magical emergence, but just through the same mechanisms that biological systems seem to use. Still talking about implications, what about ethics, the ethics of AI? The A&D framework does have interesting implications for AI ethics. If an artificial agent learns through embodied interaction, if it learns through social coordination, its ethical development could be similar to human ethics development, through understanding consequences, through social feedback maybe, through cultural transmission. That's where ethics arise for humans, isn't it? If we're emulating that, we could be taking some step in that direction cybernetically. This is more promising than trying to hand-code ethics, of course. You can't write down all the rules for ethical behavior. Think about it. Ethics is based on principles, isn't it? If you know the rules, the rule is don't go this direction on the street, but the principle is that is about one-way streets. If you understand about one-way streets, then you don't need the rules. And Tier 3 has the understanding. So does ethics have a deeper grounding in A&D than it does in other frameworks? What you can do is create conditions where ethical behavior is learned, where harm generates negative feedback, where cooperation is rewarded, where cultural transmissions, they pass on accumulated wisdom about what works. So it doesn't solve the problem of aligning artificial intelligence with human values. It doesn't solve it, but it does suggest a pathway. It does create conditions where good behavior is learned, rather than trying to specify goodness in some pure sense in advance. On the future of AI, changing the topic again here, but staying on the implications, the deeper implications of agentic negentropic dynamics. Most AI research in the last decade has focused on just making larger and larger models with more and more parameters, trained on more and more data, with more and more GPUs, with more and more energy. That's been the focus. Well, agentic negentropic dynamics is suggesting a different direction, making smarter agents that learn more efficiently from interaction. And this could be a fork in the road. One path leads to ever larger language models and deep learning systems, and it leads to turning the entire Earth into a data center battery. But another path leads to embodiment. It leads to hierarchical, locally learning agents that are more efficient and more adaptable. So, likely in the future, we're going to be using both. There's no reason that large language models can't be a component of the A&D system. You could have a Tier 3 that includes language understanding, which would be powered by modern deep learning. And you can have that interfacing with Tier 2 relational reasoning and Tier 1 sensorimotor processing. So they could work together. But an interesting question is, which approach would produce systems that are not just good at specific tasks, like answering questions, but that are genuinely agentic? that are genuinely capable of independent thought, of learning continually, of robust adaptation to novel situations, of creating and meaning through their actions. So, of course, there are obviously going to be remaining challenges. It would be misleading to present this framework as being solved. It's a promising direction, and we've made some progress on it in code, but there are genuine open problems. I mean, there's the hard problem of emergence. This framework is inspired by biology, but biology is vastly more complex. Nature is hugely complex. And a human brain has roughly 86 billion neurons, and it has trillions of synapses, and the whole thing is in some hyper-elegance, almost like supernatural elegance going on in there. Now, A&D uses graph structures with thousands or even up to millions of connections, but how do you scale from thousands to billions in a way that retains the efficiency and interdisciplinary advantages? Although this is an open question, the brain does it. Biology does it. Nature has done it. So what does that mean? That means we can do it too. We learn from nature. We can learn from nature. So it's exciting to think about, but it's still a hard problem, right? Some of the principles should scale. Hebbian learning works at any scale, doesn't it? I mean, but some might not scale. Like this interpretability advantage, for instance, that might become harder to maintain as systems grow larger, but we won't know until we get larger systems running on agentic negotropic dynamics. But again, nature has more lessons, I think, to teach us, obviously, doesn't it? Then there's also the grounding problem. This framework just assumes embodiment and closed-loop interaction with an environment. And of course, this works great for robots and agents with sensors and actuators, but what about agents that operate primarily on symbolic information? Here's a question. Can a system that learns to reason about abstract concepts, like mathematics or philosophy or logic, can a system like that be grounded in this framework? Or do we need the physics? The answer is probably yes, I think, but it's not obvious. It's not obvious how, is it? I mean, perhaps symbols themselves are learned from sensor and motor grounding. This is what neuroscience is suggesting. But there's a lot of research that needs to be done to see if we can make that work. Then there's also the temporal depth problem. Because A&D handles long temporal relationships better than standard deep learning does, but it's still limited, obviously. Can an agent learn patterns that operate over months or over years? Now, of course, this collective agency, this multi-agent, this cultural system can pass it on, but I guess I have the question, like, can it remember specific episodes from childhood and integrate those into present reasoning? Biological brains manage this, but we don't really know exactly how. This framework has tiered consolidation, but whether that's truly going to capture the temporal depth of the biological memory is still unclear to me. But all the tools here, right in the code, are here to go down that path. We have another issue, the transfer and the abstraction problem. Let me see if I can define that. Think of large language models. They have one advantage there, is that they can transfer knowledge across domains. A model trained on diverse text has learned general principles that apply to many tasks. Can agentic negotropics achieve this kind of broad transfer while still maintaining that efficiency and that interpretability that we treasure? So again, the answer is probably yes, but it's going to require further development and confirmation to define what that yes is in particular. Tier 3 principles should be domain general, but whether the current framework mechanisms for abstraction are sufficient, that's an open question. And then finally we have the last one here, is this uncertainty problem, I'm going to call it, because the framework actually uses stochasticity and noise, which helps exploration and robustness. But for some tasks, you're going to need genuine probabilistic reasoning. Can this framework handle situations where you're going to need to quantify uncertainty to say that, I'm 70% confident in this outcome? A&D can represent uncertainty implicitly, through the diversity of Tier 1 and Tier 2 patterns, but can it represent it explicitly in a way that is interpretable and that can be communicated to humans? There again, another open question. Now all of these, I'll just roll through them again. The hard problem of emergence, the grounding problem, temporal depth problem, transfer and abstraction problem, and uncertainty problem. I, in my enthusiasm for agentic negentropic dynamics, have great hope and confidence, but these would be great research branches to tracks to go down. So in way of conclusion, what have we explored? Okay, let's just take a stock of what we've covered. We started by identifying some fundamental problems. Machine learning systems, whether they're traditional or deep, they do have significant limitations. Legacy machine learning is rigid and hard. It's handcrafted. Deep learning is brutal. Deep learning is energy and data hungry. But we then introduced an alternative approach, which is agentic negentropic dynamics. This was a framework that's inspired by how biological brains actually work. Now, the core of the framework is a three-tiered hierarchy. Tier 1 for immediate reactive processing using local learning rules. Tier 2 for pattern recognition and flexible reasoning. And Tier 3 for abstract principles and for consolidated knowledge. Now, the system learns through embodied interaction. It uses local plasticity rules, which are inspired by neuroscience, and there are multiple tiers which allow simultaneous learning at different timescales, and of course neuromodulation gates learning based on context and needs. So that's a rundown of agentic negentropics. Now, the result is a system that can do, let's just say 7 things. Number 1, it can learn from a few examples, so that's sample efficiency. Number 2, it can learn continuously without forgetting, so that's, continual learning. Number 3, it can understand causation and not just correlation. Number 4, it can adapt robustly to novel situations. Number 4, it can run on modest hardware with low energy consumption. Number 6, it can coordinate and learn with other agents, so, collective intelligence. And number 7, it can generate interpretable decisions, not black box. I would even say, not even white box, I would say glass box decisions. I mean, it's all physics-based, and, it's all queryable. It isn't a cure-all. For some tasks, obviously, deep learning is still going to be superior. And then for narrow problems with clean data and unlimited compute, you might want legacy approaches. They might be better. But for embodied agents, learning continuously in complex and in dynamic environments, the A&D framework has genuine advantages. As a matter of fact, I would say that there's going to be a conjoining of these systems in the future. But it does matter, and here's why. Why should we spend pages explaining an alternative to machine learning? Well, because how we build AI systems is going to affect what they're capable of, right? It's also going to affect how we can interact with them, whether we can trust them, and ultimately what kind of world that they help us to create. So deep learning has achieved impressive results, but it's created a world where, first of all, AI systems require massive compute, which is only accessible really to large corporations. So there's a kind of a monopoly there, isn't there? The capture. Then also, reasoning is opaque. Reasoning is uninterpretable in deep learning. And then thirdly, systems are brittle. And fourth, the learning is single task. Learning is not continuous. So there's that. And then understanding is just impossible. All we have is prediction. We don't really have understanding in deep learning systems. What agentic negentropics suggests is a different possibility where you'd have a world where your AI systems can run on edge devices that are decentralized and distributed. That would be great. So you break the capture, right? You've got reasoning here, which is interpretable and tractable. You've got systems that are robust and adaptive. With A&D, you've got learning that's lifelong, that's integrated. And then the systems don't just predict, they actually do understand. Now this has profound implications, really. Decentralized AI could be more equitable than centralized models. Interpretable AI could be more trustworthy. Adaptive AI could be more useful in real-world environments. Embodied AI could bridge the gap between abstract reasoning and physical reality. And of course, when you think of sustainability and environmental concerns, just the energy efficiency alone is worth a hard look. But in the bigger picture, on the deeper level, this framework is part of a larger conversation about what intelligence is, and also about how intelligence actually emerges. For much of the 20th century, intelligence was treated as something separate from life, kind of an abstract reasoning that could be captured in pure mathematics and logic or something, and divorced from bodies, divorced from emotions, with no connection to any embodiment. And we think that this view has led to systems that are really good at specific logical tasks, playing chess maybe, but they're terrible at embodiment. They're really bad at adaptive reasoning, the type of reasoning that biological intelligence displays. So we think we've gone down a narrow path with blinders on, in a sense. Over the past few decades, though, that view has gradually shifted. Neuroscience is showing us that thought and body are both integrated. They're deeply integrated, actually. Psychology has shown that emotion and reason can't be separated. Ecology has shown that organisms and environments, they actually co-evolve. That the organism shapes the environment and the environment shapes the organism. And complexity science is showing us that intelligence emerges from interactions. Intelligence is not centralized control as we're used to thinking about it. Intelligence is emergent from interactions with the environment. So agentic negentropic dynamics is just an attempt to embody this newer understanding in a computational system. We're just saying that intelligence is not abstract reasoning that's disconnected from the world. Intelligence is embodied action in an environment, learning through interaction, creating order, and building meaning. So this is a vision of intelligence that's more grounded. I think, personally, of course I'm biased, but it's more realistic. It's ultimately more interesting than the older views, and it might lead to systems that are more powerful in practice, even if they're not as flashy as the language model is. A language model that can write poetry. So here's an invitation to think about. This framework isn't complete. We have really strong proofs of concepts, we have applications, but what we've outlined mostly is the ideas here, and we've shown how these ideas could work, but there's a lot that still remains to be done on it. Now there are theoretical problems to solve too, implementation challenges to overcome, benchmarks to run. There's a lot of work to do. But this is not really the point of this explanation. What I'm saying here is that we're just offering a different way of thinking about intelligence and about machine learning. It's a way that's inspired by how life actually works. It values efficiency, it values interpretability. We're valuing adaptation too. This is a way of thinking that sees intelligence not as disconnected from embodiment, but as fundamentally grounded in embodiment. Now, if you're involved in any AI research or development, if this framework offers alternative approaches that you think are worth exploring, and if you're interested in biology and neuroscience, A&D offers a way to think computationally about how brains work. If you're concerned about AI safety or AI alignment with human ethics, then agentic negentropics offers a perspective on how values might emerge or evolve instead of just being imposed from the outside. And if you're simply a thoughtful person, you're trying to understand the world, agentic negentropic dynamics offers some perspectives on what intelligence is and what it means for systems to act meaningfully in a complex world and to leave a legacy in their world lines, either individually or collectively as collective agents, like families or organizations. The real value of this framework is not that it is definitely right. The value is that it opens a conversation about alternative approaches, grounded both in biology and in practical reasoning about what actually works. And I think the real value is that it's applicable. It's practically applicable now. You can code it up. It's mature enough to be implemented in the moment. But the vision is a future where robots in homes learn continuously by adapting to their family's needs without needing massive data centers. This would be where a household robot learned by living with you. It learned by growing and understanding over years without ever connecting to the internet or without ever uploading your private data to distant servers. Right? This is local intelligence on board. Also, there's a vision of scientific systems that design and run experiments. They learn causal relationships, they discover new principles without human guidance, where humanity's best researchers are working alongside AI partners who are truly partners. They're not black box oracles, but they're colleagues. It's like a true human AI collaborative, hybrid, operative collaboration. I'm thinking also a vision of a future that has these communities of agents. Yeah, robots, but also perhaps artificial agents operating in digital space as well. And they're developing a culture, and they're developing wisdom, and they're passing knowledge across generations, making intelligent collective decisions while remaining interpretable to humans. Think of a network of Tier 1, Tier 2, and Tier 3 intelligences, and they can share across. You could actually firewire one to the other. You could have them log into a network and update based on collective knowledge or knowledge of pan-generational knowledge. It's just really interesting to think about. They would also be making intelligent collective decisions, while at the same time they would always be interpretable to humans. I'm also thinking of a future with embodied AI tutors that learn to teach children or even adults as individuals, that would adapt continuously, understanding not just what the individual knows, but how that individual learns best, and fostering not just knowledge but also character, also wisdom. I'm also thinking about a future where AI is not centralized in a few massive models, just in a bunch of data centers, but AI is distributed, AI is diverse. There would be millions of specialized agents, each operating locally, each learning from interactions, each contributing to an ecosystem of intelligence. This vision might sound utopian, might sound idealistic, and there are genuine challenges between here and any of those goals, but the framework outlined here, it suggests that it's not impossible. And the principles are sound. They're grounded in both neuroscience, practical reasoning, physical law, physics, and there are some engineering challenges, but although they're real, they're surmountable. Then the economic and social implications would also need careful thought, but the direction is promising. That's what this conversation has been about. We're not trying to prove that this framework is superior to everything else, but we're showing that there's a pathway here, there's a different path, and this path is inspired by how nature solves problems of intelligence. Again, look at us. The evidence is here. What's happening between your ears is something we can learn from and something we can emulate better. We can do better. It's so efficient, isn't it, nature? So this path might lead somewhere worth going.